Hello, all. This is Kritika from the Department of Electronics and Communication Engineering. I'm from M. Kumaraswamy College of Engineering. Today, I will be discussing NAND and NOR gate and why they are known as universal gate. Digital electronics is built on logic gates. Common logic gates we know include AND gate, OR gate, NOT, NAND, NOT, HEXOR, and XNOR. Among these, NAND and NOR occupy a special place because they are called universal gate. A universal gate is a gate that can be used to implement any Boolean function. This means that if we have only NAND gate or only NOR gates available, we can still build any digital circuit. Because of this capability, these gates are extremely important in digital system design and integrated circuit manufacturing. In this presentation, we will first understand the concept of universal gate, then prove why NAND and NOR gate are universal, and finally solve a practical example using NAND implementation. A universal gate is a gate that alone can be used to construct all other basic logic gates and any Boolean expression. For a gate to be called universal, it must be capable of implementation of NOT gate, AND gate, OR gate. Once these three operations are available, any Boolean function can be realized. NAND and NOR gate satisfy these requirements. By connecting the NAND gate in different way, we can generate NOT gate, AND gate, and OR gate. Similarly, we can also using only NOR gates, we can also generate three basic gates. This property reduces the hardware complexity because manufacturers may use only need one type of gate for building large number of digital systems. To prove that NAND is a universal gate, we must demonstrate that NOT and OR gates can be implemented using only NAND gates. We already know that Boolean functions can be expressed using a basic combinations of AND, OR, and NOT operation. Therefore, if NAND gate can generate these operations, then any Boolean functions can be generated using NAND alone. This proof is important because it forms the theoretical foundation for universal gate implementation. In upcoming next few slides, we can construct how NOT and OR gate using only NAND gates are possible. And this is the slide representing implementations of NOT gate using NAND gate. A NAND gate generally perform the operation that, for example, if A and B the input, then A NAND of B gives the output AB the whole bar. If both inputs are connected together, then A NAND A, which gives the output of A dot A the whole bar. Since A dot A equals to A, the output becomes automatically A bar. This is exactly the NOT operation. Looking at the truth table I have given in this slide, when input A equal to 0, the output is 1. When input A equal to 1, the output is 0. This matches the behavior of inverter or NOT gate. Therefore, a NAND gate can be a function as a NOT gate simply by connecting its two input together. From this slide, I can say NAND can produce inversion without requiring a separate inverter. And this slide implementations of AND gate using NAND gate. Let us implement an AND gate using of NAND gate. A NAND gate gives the output AB the whole bar. However, we need AB. To obtain AB, we can pass the NAND gate output through another NAND gate configured as a NOT gate. Mathematically, you can say this as AB equal to AB bar the whole bar. So the first NAND gate generate the complement and the second NAND gate remove the complement. Look at the truth table I have given here. For the input of 0, 0, the output is 0. And for the input of 0, 1, the output is 0. And for the input of 1, 0, the output is 0. And for the input of 1, 1, the output is 1. This resulting the circuit behavior exactly like the AND gate. In the slide implementations of OR gate using NAND gate, let us completely we can create an OR gate using only by using of the NAND gate. The implementation is based on the De Morgan's theorem, that is A plus B equal to A bar, B bar, the whole bar. First, we can generate A bar and B bar using only of NAND gates acting as a NOT gate. Then these inverted signals are applied to another NAND gate. The final output becomes A bar, B bar, the whole bar equal to A plus B, which is exactly the OR gate. This demonstrates how Boolean algebra and De Morgan's theorem simplify the logic design. Here, the De Morgan's theorem is one of the most important tools used when converting the circuit into NAND only or NOR only implementation. In this presentation, implementations of OR gate using only of NOR gate, now we completely switch our focus to NOR gate. A NOR gate perform A plus B the whole bar. To create the OR gate, we simply invert the NOR output. This is done by passing through the output through another NOR gate whose inputs are used to tie together. The first NOR gate generates the complement of OR and the second NOR removes the complement and restore the original OR function. Thus, OR can be implemented using only of NOR gate. From this slide, I can conclusively say just as a NAND gate, we can also recreate the NOR gate by using of OR gates. Implementations of AND gate using NOR gate. Now we can implement the AND gate using NOR gate. Using De Morgan's theorem, AB equal to A bar plus B bar the whole bar. First, we generate the A bar and B bar using NOR gate and configured as a NOT gate. Then, these complemented signals are fed into the another NOR gate. The resulting output becomes A bar plus B bar the whole bar equal to AB, which is exactly the AND function. This proves that NOR gate can generate AND operation. Again, here also De Morgan's theorem makes the implementations possible. Now we can move on to the implementations of the NAND gate using NOR gate. Since NOR gate can create both AND gate and NOT function, they can also create the NAND function. This process is straightforward here. First, we have to create an AND gate using NOR gate, then invert the AND output using another NOR gate. Mathematically, we can say this as NAND equal to AB the whole bar. This construction demonstrates the flexibility of NOR gate and further supports the claim that NOR is an universal gate because NOR can create NOT, OR, and NAND. It can implement any Boolean function. Out of this, we can explain, now we can solve this with a practical example. Here, the Boolean example is given for NAND logic implementation. The Boolean function is f of a, b, c equal to summation m of 0, 1, 3, 5. The first step is to plot this min terms on a K-map. We know that how to solve the K-map, right? The cells corresponding to the minterm 0, 1, 3 and 5 are marked with 1. Now we can form the largest possible group from this K-map. From this grouping, we can obtain the simplified terms for this final output. The final output we have get from the simplified K-map expression is we get the output as A bar B bar plus A bar C plus B bar C from three different groups we have get in the K-map. And next one is by using that Boolean function, and by using of that Boolean function, we have to implement this by using only NAND OR implementation. By using of only AND gate and OR gate, we have to implement that expression in a circuit format. After applying the expression, F equals to A bar B bar plus A bar C plus B bar C, we can implement by using of this conventional and OR logic. First, NOT gates generated A bar, B bar, C bar were required. Then three AND gates generated the output A bar B, and the second AND gate generated the output A bar C, and third AND gate produced the output B bar C. Finally, the outputs of these AND gates are combined using OR gate. This is the standard sum of product implementation. Although the circuit works correctly, it uses multiple gates. like NOT gate, AND gate, OR gate. In integrated circuit design, it is often desired to use only one gate type. Therefore, we convert it into NAND form. Finally, we convert the circuit into NAND logic gate. We apply double complementation starting with F equal to A bar B bar plus A bar C plus B bar C. We introduce a double negotiation bar by using of this De Morgan's theorem. We can implement this NAND logic to the above mentioned AND or logic circuit. Now, every product term is generated by the NAND gate. The output of these NAND gates are then fed into the final NAND gate. This product, the original function while we're using only NAND gates. This design is preferred in practical digital system because NAND gates are inexpensive. NAND gates are very easy to manufacture. Larger circuits can be built using a single gate type. Troubleshooting and fabrication become simpler. Finally, from this learning, we have learned what is universal gate and why NAND and NOR gates are called universal gates and how NOT and OR gates can be implemented using NAND and NOR gate and how to simplify a Boolean function using KMAP and how to convert an AND or realization into NAND implementation. These concepts form the foundations of combinational digital circuit designs. Thank you.